Hello everyone, my name is Amir and today I will talk about a paper by DeepSeek Research AI Group named mHC Manifold Constrained Hyperconnections. As a really short abstract in this paper, uh, they are expressing that in multi-stream residual connection blocks, this kind of architectures provides us some benefits, but also they cause some instabilities. They try to solve this problem geometrically. And firstly, just to understand what's the problem, let's start by, is it possible to? Yeah. Let's start by residual connection block. As you can see here, at the very first, we have an input signal. We pass it through a layer F or a couple of layers. And at the end, we add them together and pass it through the next kind of layers. Here's the equation. As you can see, if we make this part zero, it's an identity mapping, and it enables the gradient flow easily. It's stable, and if we stack a couple of these layers on top of each other, uh, the gradient is stable and it's actually conserving deep signals. So it's possible to scale this residual layers more than 100 layers on top of each other. And as you can see on a scale, when we have a couple of layers, even if this part becomes zero, its identity and the gradient again flows easy. But the problem is that recently micro architecture designs expand this residual streams. So the question here is that can we increase expressivity without breaking identical mappings? And uh, here you can see some new architectures of residual blocks. Instead of one input signal, we have multiple embeddings, hidden embeddings of the same signal. Like imagine like in a transformer or a vision transformer, we have a couple of hidden embeddings for the same token. It's important for the same token, and we want to compute attention and everything based on different contextual hidden layers. So at very first we have n number of signals, exactly standard residual block. We have this path. Here we have a pre-mapping, which we apply this mapping before that layers like attention could be here. And we have a post mapping. And in this residual path, we apply a res mapping, which is important. And at the end, you can see that the formula to get the output is something like that. Here you can see the dimensionalities for pre and post mappings and also res. It's really cool because as you can see, the dimensionality of pre and post is 1 by n. Here we have n by c. Instead of one channel in the standard residual block, we have n channels. And when we apply this block to all of these layers, it becomes the same as the input to this layer in standard residual block, 1 by c. So the computational cost, we actually are increasing topology without increasing any floating operations. The operations, the most complex part is here, and the computation is exactly the same. And after that, we again kind of expand that and add it to the output of this residual path. And this residual mapping, as you can see, is n by n, so it doesn't change the dimensionalities. And the point is that it learns how actually streams mix. We have different hidden layers, and it learns how different embeddings, different kind of contextual embeddings contribute to each other.
Sorry, I have a question. What is the purpose of the normal stream, not the residual stream? Why is it using a single channel approach or something?
How does it work?
Yeah.
It's we have like one, imagine like we have one token, or in neurons we have one input, and we pass it through the residual block. We add it to the previous layer's output. Okay, it's only one value. But here we have like a set of hidden embeddings for the same value. Got it? And actually, more complex than that a little. And this architecture buys us some benefits. Firstly, it decouples residual width from compute flops, floating operations, because we are doing all of these processes, but the most computationally complex part here is the same. We are increasing routine flexibility in this mapping part. Different hidden embeddings can contribute to each other, exchange information, and we are improving performance as they show in their paper, hyperconnections. But the problem here is that hyperconnections removes a strict identity mapping. If I show you here, we have identity mapping. If this part becomes 0 after like 100 layers, the input signal and the input signal to the last layer is the same. But here we don't have something like that, because we have a coefficient before input layer, so it could make a problem. So let's see where these things could go wrong.
So can I ask a question? Can we go back to the architecture slide? Can you explain what is C and what is N?
C is dimensionality of data. Like in a token, in a sequence, a token has an embedding, right? Like a vector of 128, right? This C is that one, and for each token, we want to have like 10 embeddings for the same token, 10 hidden embeddings for the same token. That N is 10. Okay, something like this. So here you can see the formulation. If we stack a couple of these layers on top of each other, multi-layer, it would be the formula to get the results. As you can see, we are doing a product on all of these residual mappings. So it's better to focus on this part, because if we want to compare the identity path in ResNet and hyperconnections, we can see that as I said, if this part becomes 0, it's identity. The gradient flows easily. But here, for large mapping values, for large and small mapping values, this identity part, would approach to infinity or 0. So it can really amplify or attenuate the input signal. And when in a scale, when we have a large number of layers, it could kind of kill or really amplify the input signal. So we can kind of as a result say that residuals work because identity is preserved, but in hyperconnections it destroys, because that cannot guarantee this situation.
Before you go, do you understand what is this about?
So it's kind of like a network that has residuals, but then it's like many of them together, like these hyper.
Yeah, exactly. Exactly. A multi-stream actual residual. Yeah, something like that.
No, but do you understand
Uh-huh.
what is dangerous and why is dangerous? There's like what is happening
You
in
can
this
lose
formula.
identity. You can lose identity as your model gets bigger. You can lose the ability to make identity transformation with this network.
Why it is interesting? Yeah, what
It's a caveat. I think it's like a caveat.
I don't understand what you mean.
Because it's exploding gradients. I'm assuming, right?
It could, yeah. But the gradients and
Well,
also
but what is the
paths.
gradient? So can you skip back to the identity? Can you take a derivative to that a normal formulation?
Of course.
Yeah, this one. XL plus 1 equals XL plus F. What is the derivative of this expression with respect to XL? One plus something.
Plus something.
Yeah. But then it's always one. It's always like when you have multiple layers stacked, you just have 1 times 1 times 1 times 1. So it's always 1. But can you go back?
Go back?
Yeah, to your last slide.
Oh, sure.
On the screen. Yeah, here line 2, X capital L equals this product when you take a derivative, it's just that product. And if one of them is 0, no derivative, nothing propagates. So it's very simple. Calculus 101 first class or something.
Yeah.
It's like but the rest is just to scare you.
Exactly.
It's just like it's one line, linear functions. That's practically what is happening. You see some little problems. Yeah, okay. So it's just the derivative of this term. Derivative is a linear operator. So derivative of the sum is sum of the derivatives. So forget about that. Nobody cares about this one. Just this one. And that's basically the thing. One layer, another layer, next layer. But we are evaluating the products.
Yeah, exactly.
And before you were multiplying 1. Now you're multiplying this coefficients. And those coefficients may explode or may collapse, or like we're back to the original problem.
Yeah. So yeah, that's the problem, and we want to fix it. Here, just to see, what is happening. Here you can see that if we want to compare, the absolute loss gap between HC and mHC, the current method, you can see that in here, like step 12K, we can see that loss spikes. And about the gradient norm, you can see that there are some explosions. And also, what's important here is that how much we are amplifying the signals.
I know how to fix it.
What?
I know how to fix it. Let's add an identity.
Add an identity. Yeah.
That's it, fixed. So instead of replacing,
yeah.
So we had X plus F.
Exactly.
And we replaced X. Well, leave X plus F and add your H times.
What we don't know about the rest of that. If that part becomes large, it will again explode, right?
No, it will not become large because the X will stabilize it. If you remove X, you have if you just do F, then there will be unstable behaviors.
Yeah.
Like that. But if you add just F, nothing else, just F of X, blah, blah, then you will have similar behavior. You add X, none of that behavior, because your gradient always reaches there and stabilizes. Even if in between something broke, the gradient flows back. Okay, they probably they wanted to fix it a different way. Okay.
Yeah. Okay, and about Amax, like how much this residual process is amplifying the input signal. we call it AMAX, maximum absolute signal amplification factor of matrix. It's like just row sum and column sum of the trace matrix. And in hyperconnections is 3000. That is a lot. It's like making input signals 3000 times larger, as you can see here, in comparison with the this current method that we're talking about. It's so larger. And so what we need, how we want to solve this problem. Firstly, we want something that does actually information mixing across streams, like is happening in hyperconnections, and we need depth-wise compositional stability when we stack some layers on top of each other, something like this problem. That happens. If I want to show you here, you can see that in single layer, we don't have any, AMAX change. It doesn't amplify the input signal that much. It's the same. But in actually composite mapping, when we have a couple of layers, you can see that it's here. You can see that it's not doing well. And the third one is that we want to preserve this identity mapping and generalize it. So we search for a manifold. If we can make a, constrain all of these mappings, maybe we can solve the problem. And this manifold should be closed under multiplication, because we are stacking some layers on top of each other, and these mappings we are actually multiplying them together. And also about the spectral norm bounded. The spectral norm is the largest singular value. It shows us how a vector, how this kind of mapping is the kind of stretch factor of the matrix, how the maximum stretch factor of the matrix, and also allows expressivity, like this hidden embeddings be able to contribute to each other. All of these parameters that we said, this leads us to Birkhoff polytope. Of course.
Can you explain what is closed under multiplication means here?
Yes, I will explain that in the following in a slide. About it's obvious that we don't want to use these raw mappings, so we have to project them onto actually a manifold. And this part we are actually doing this projection, and we want to define it something like this. The mapping, the dimensionality of mapping is n by n. We want all of the rows, the sum value of all of the rows become, the sum value be 1. So in that case, we have a stable forward pass, and the sum value, the column sum, actually something like that, is 1. So we have a backward, a stable backward process, stable gradient flow. And also all of the entries be larger or equal to 0. So in that case, it's a convex problem. And this thing is this is actually all of these mappings could be part of doubly stochastic matrices. And the set of all of doubly stochastic matrices is Birkhoff polytope, that they are convex, as we said here, and they are doubly stochastic with these two things. And we want is to constrain this mappings to a manifold that is doubly stochastic. And why double stochastic works? Here we can see that for any double stochastic matrix, the spectral norm is less than or equal to 1. It means when we have a signal, we have an input vector. It doesn't stretch that vector. It doesn't enlarge that. So the spectral norm is 1. Therefore, when we stack all of these layers are on top of each other and compute the product, in that case, it's also the spectral norm of all of them. The product is less than 1. So it shows that it's on the same manifold.
Well, but then vanishing gradient is possible.
Vanishing gradients.
Less than 1. Each one is less than 1, and you have L of them, and you
What do you think?
it costs small. 0.9 times
Yeah,
0.9
that's
times
possible.
0.9 times say.
Yeah.
Exploding is not possible, but
Exactly.
like if it's equal to 1, then it will stay. But if it's less than or
Yeah,
equal,
it's
it can vanish.
no, I think because column values, because in double
It's
stochastic,
less than or equal.
yeah, it's less than or equal.
That's what I'm like. Yeah, is it equal maybe?
No. Actually, they are using a method to make it, closer to 1. Okay, I will talk about that.
Yeah. Okay, but if it's
Okay,
less than 1,
if we
it's
can,
less than 1.
yeah, at the end, less than 1 is less than 1. And yeah, so this ensures non-expansive propagation, but maybe,
Yeah.
yeah,
That's what
exactly. So, the forward signal gain is bounded. And about the backward propagation, because this spectral norm, passes through transpose, we can say that also the backward propagation same bound applies. And this is the mathematical reason that we can say this Amax drops from 3000 to around 1.
well, solves explosive.
But not
like vanishing.
Yeah, not vanishing. So about as a key geometric property, if A and B are doubly stochastic, you can say that AB is also doubly stochastic. So when we compute the a product of all of these mappings together, it's also belongs to that manifold, and it's belongs to Brikov polytope. So this preserves rouse sums equal 1. It helps in forward pass, columns 1 in backward pass, and non-negativity, which
But the
enforce it
gradient
too.
update doesn't have to preserve it. Are they doing how do they ensure it stays on the Birkhoff polytope? Each of the
They are doing a iterative process, sinkhorn, NOP. I will explain that. That's real simple.
so they like optimize and project.
Yeah.
Okay.
Yeah. Actually, no, I will explain it. Yeah. So yeah, that's identity mapping generalized to kind of convex mixing. And based on all we have said so far, we can, they propose this architecture here. This is the main architecture of mHC, this paper. And here is the process. As you can see, we have 3 mappings here. Just we have added some parts here that we project these mappings to manifolds. And firstly, we flatten residual streams, all of these layers, all of these actually N by C matrices to 1 by NC. And after that, we apply root mean square norm, root mean, yeah. And Then on all of these mappings, we have this part that we have a projection matrix, we have some scalar gates, and some biases. And for pre and post mappings, we apply sigmoid. This one is scaled. And to make sure about that manifold, to kind of enforce it about being doubly stochastic, we apply this Sinkhorn knob algorithm, which is really simple. And yeah, here we can see that the kind of formula is the same as HC, not mHC. And yeah, here you can see the Sinkhorn knob
You can move it.
projection.
You can click on more.
Oh, okay.
You can click on
Okay.
more and hide.
Oops.
Yeah,
Share. Sorry.
no. Click on more
Uh,
and hide it. Hide floating controls.
Hide.
The last one.
Oh yeah. Okay. Good. Yeah. Sinkhorn knob projection. We start with exponential values of this mapping, because we want them to be greater than 0, and we do this iterative process. One time we normalize, we do column normalization, just divide the values by the values of each column by column sum values, and then row normalization, the same process on rows. And they do this process maximum 20 times.
It
So
differentiates through that.
yeah,
Through 20 steps.
exactly.
They claim they're like as efficient as before because they like blah 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 did something else. There.
Yeah, it's not efficient at all. It's not efficient at all. Yeah. And even after 20 iterations, they cannot guarantee that.
Converge.
Yeah.
I have
So
a question.
yeah.
In this first line, you write that it's an exponential
Mhm.
matrix.
Yeah.
So is it a matrix exponent or
No. They sell it twice.
Yeah, exactly.
It would be too expensive to do major.
Yeah.
Okay.
Yeah, this fancy name is for just this simple method. And
You don't have to do SVDs or
so yeah, after that 20 maximum 20 steps, in ideal condition, we can guarantee, we cannot guarantee, but maybe that
it's closer.
it's closer. Yeah, but in worst case scenario,
But why not just Wait, come on. Leave it here. I'm sure this is how it will be done in practice.
I will try that. That's really cool idea. No, I will try that. That's
No, this is how it will be done. It's just because the importance of that, like the advantage of this and the simplicity of the skip connect.
Yeah.
Skip it. Well,
Yeah, okay. And yeah, in backward gain, again, in worst case scenario, we can say that column sums is maximum of the column sums is 1. So empirically we can say that composite gain, that Amax thing, is less than or equal to 1.6, and in comparison with 3000 is much better. And as you can see here, for single layer, obviously we don't have any problem, but about composite mapping, for HC it was 3000, but here you can see that it's most like 1.6, something like that. And in forward and backward signal gain, you can see these two things. And yeah, at the end, to just compare these all of these things that we have said, in HC, we had high expressivity, but no spectral constraints. We were not bounded. And in residual, we have full stability, but no mixing. We cannot scale the number of hidden kind of embeddings. But in MHC, we have convex mixing. Actually, these hidden embeddings can contribute to each other, and spectral bound, kind of. But so at the end, we can say that manifold constraint act as a geometry regularizer, and as a conceptual takeaway about what so MHC reframes residual architectures as a depth-wise Markov mixing process constraint on manifold. This process, we do it iteratively. It's like a Go process. So yeah, I'm done.
It was a short presentation, yes, but that was good. Thanks.
Mhm.
But what did they gain? Like, I didn't see much experiments though. Like, I just saw
Mhm.
more about the problems
Yeah.
of this approach. But like, what did they gain? Because I mean,
Mhm.
harder to train, I assume, computationally.
Yeah.
But was it better performing?
Mhm.
Do you have those results, or
I don't have those results in, my slides, but they have done like in on 3 data sets. I have seen that 3 or 4, and the results is much better than HC when we have, in scale, when we have uh, more than like 50 layers. They have expressed, because I read that paper 2 weeks ago. Because of that, I don't remember exactly the numbers about this part, but it was better.
but like what I would like to see
Mhm.
is why all of that complexity. What did it bias, right? Okay, you don't link the paper, but it's
Oh yeah, I did.
see. See. Maybe let's look at the paper. Can you pull it up? Do you have the paper?
Yeah.
Can you look for
Oh, here, yeah, I can.
Yeah, you can still keep sharing.
HC.
Maybe we can just pull the results and see.
Many.
Yeah. So if you at least we can make the results.
And what is the advantage of these like hyper connections? Is it some kind of interpretability, or like why do we need those? Because I understand they tried this and it wasn't like
Yeah, like
very
see your presentation.
and then they use this mHC.
Yeah, but it's answering your question. Yeah, in like
Lower. Is there some kind of a trade-off for this like manifold stuff?
yeah, it's a kind of trade-off, but the point is that like in current complex LLMs, or like vision transformers, when we want to, in like attention mechanism, when we have only one embedding for a token, it's like we are comparing each token with other one, uh, you know uh, from a single kind of viewpoint contextually. But if we expand that, like we have multiple hidden embeddings for the same token, for the same word, it's like we have, more kind of viewpoints to compare these words with each other. In that case, if we have, if we expand this embedding from 1 to n, it's like we are helping the model to understand this similarities better. Yeah. Sorry.
Yeah, let's see in results. Well, the tables. Why would
There is one table here and some
why would I go through all of this trouble? Like, what am I gaining? The results are not exciting.
Method slower than the regular HC method?
yeah, it is.
Okay.
Yeah.
Well, but even regular HC is just adding that H, right? And then you have the explosion problem as they show, right?
Mhm.
But H is why, your previous question was, why would you even add H? I think we just want more parameters in the model without affecting as much computational load. Because more parameters, maybe it can remember things better, maybe it can train better because gradient is easier. Gradient flow easier to escape different landscapes. Landscape is smoother basically in high dimensions.
Maybe it's not really compatible with these hyperconnections of multiple channels. Maybe like different age, different subparameters to make a residual for the counterpart that went through the proper cycle.
Well, in original skip connections, parameters were only in the gating function. Like, okay, if we're not using the gating function, it's always open, then we have no parameters, then we have ResNet. Here, they didn't go back to the gating function, but they just like, oh, this will be also an MLP, basically, a linear layer. That's what they're doing. They're saying, okay, this is a nonlinear layer, this is a linear layer. Back to, and calling it hyperconnectivity is a marketing trick, frankly. I mean, it's just two branches. One is a linear layer, transformerized, right? Self-attention and MLPs.
Yeah.
Just a linear layer, those branches. Okay, we did that all the time. So, but then again, my question is, why not this?
I have a question. Does that column-wise normalization fix the gradient vanishing problem?
They're saying no, gradient norm is less than 1.
Less than 1.
Potentially. Less than or equal. Can be equal. When it's equal, it doesn't matter. But when it's less than 1, multiply 2 of them, and the norm goes down. If one of them is less than 1.
Yeah.
If both of them is less than 1, it goes down faster. It's just like squaring or power n of a number less than. Yeah.
Whatever I'm thinking about, it's
And well, so I don't see results. I just see this kind of like what I'm trying to see is why go through this trouble? What are we gaining in practice? I understand. I mean, we can keep saying that, oh, potentially more parameters, scaling low, blah blah blah. But I mean, does it help?
One of them that
I don't see it. I don't see results at all. Like we had 20% accuracy, now we have 27. Like, where is that? And also, I don't just for students for sort of like the little thing. This is biology, right? One case study. This is one loss curve that we got. Here's we're showing to you. There's no analysis of statistical stability of any of that. No error bars or nothing. I mean, we are in biology era, zoology era of AI, right? That's okay.
If you look at figure 8, though, I think what they're trying to show with this mHC is like, figure 8, they're showing like there's more diverse. I think there's like more diversity in like these hyperconnections. Yeah.
Well,
yeah, there's
what does it mean?
Like there's a utility in using these hyperconnections because they're giving like some different perspectives of the data in some way, as opposed to the regular residual connections.
Then what's the goal? So we're paying a price. What are we paying it?
Yeah.
And we're paying a price. We have more parameters, more computation. Like, yeah, that's what I'm like. Why are we doing this? I mean, it's fun, but
we actually had two problems, right?
Which problem?
Like input amplification and attenuation, right?
No,
It
I
got-
didn't have any problem.
Isn't it a problem?
I had no problem. Like from the start. Why did we start here? Like why did we add? We thought we will gain something, right?
Yeah.
But do we? In the case. Do we gain anything over this one? Before like diving into any of that, like I would like to see.
Oh, got it.
Right, like why are we complicating things?
Even not this one, comparing ResNet with HC. Yeah. Yeah. Got it.
Why are we complicating things? There should be a reason. There must be a reason. Or simpler is better.
In the other paper, HC, they have shown some results that is better than this, but because that was the other paper, I didn't show the results, because of that I just.
Does it learn faster? Doesn't like learn?
Which one? HC then?
HC, yeah.
Probably not.
Then gradient. So it goes lower or something.
We are adding more parameters, but the most complex computational part is the same, right? That F is like
F
is the same.
Yeah.
But we are adding
of HC. Well,
yeah,
but
that's
also pre and post are costing you as well.
Yeah.
Yeah. But I wouldn't like. This is not a conversation to have. It's like, hey, look, we added a lot of computation, but it's just a little bit. But
yeah,
add zero computation if you don't give me anything in return.
Yeah.
Like, why would you even add any computation?
Yeah.
It's kind of like we introduced a problem, then we solved the problem, but there was no problem. It's like that. I don't know. I don't like.
Yeah.
It's like I didn't read it, and that's why. That's kind of like self-sustaining process. That's but very cool. Thanks for the talk. Any other questions? I think
If you could summarize the novelty of the paper in 1 or 2 sentences.
The novelty is that in multi-stream residual connections, it provides us some benefits, but it also caused some instabilities.
previous work.
Yeah. This paper, this method is trying to solve that. Not about ResNet, about this HC.
Does it achieve to solve?
Does what?
Does it achieve this goal?
Yeah. In a scale when we have large number of layers, saying that okay, probably.
Asked Gemini why would we need to use some kind of H in the first place? And it reasons that maybe needed for the cross-channel interactions that they are talking about.
That's fine. My cross-channel interaction. What are they giving us?
If you trust user identity, then you are not mixing the residual.
Why would I care about me?
I don't know.
Yeah, and it's like you're telling me, oh, this is valuable. No, it's not. I don't care about it. It's like, is this something that is inside? Like, okay, well, so they mix now, or they don't mix now. What I'm losing, what I'm gaining. I'm like, see, like the other problem should be solved.
Yeah.
And this is more of like, no, but then your car will be not a white color, but red color. Will I go slower or faster?
Yeah.
No, nothing will change.
Yeah. Before that DeepSeek architecture that came out, it was like when we add more parameters, when we add more layers, more complexity, the performance would be better. Right? Maybe this approach.
Well, it's
like
just
that,
like
right?
how can we infuse more parameters
Yeah.
into the model? But then show me the gain. So the log plot, right? We're over there already, somewhere on the tail of it. Is our gain like 0.1, like what are we gaining for that?
Yeah.
I don't know. I just don't know. Yeah.
Okay.
So, but it's a question that would be interesting to answer. Okay. Okay, but that's a good presentation. So, let's take one.